So let's return to this picture we had of the sun, which has the capability of converting protons, that is, a hydrogen atom without its electron. And the reason that protons are the reactant here is that the temperature is so high inside the sun that the electron has been separated from the nucleus. So what it leaves us with are protons. And the final product is normal helium. So this conversion then of a proton to helium-4 is what occurs in the core of the sun. And as we mentioned before, the temperature of the core is some 10 to the 8 Kelvin. But emitted from the surface is electromagnetic radiation. And electromagnetic radiation moves with the speed of light along the direction of the flow of that energy, and it's comprised of an electric field and a magnetic field. And you can rotate the electric field into the magnetic field with your fingers with respect to your thumb, rotating the fingers into the thumb, and your thumb points then in the direction of the travel of electromagnetic radiation. But what's remarkable is the simplicity of the Stefan Boltzmann law comes from the fact that we are basically looking at the oscillation of the electron-nuclear interaction that comprises all material. So if we extract that for just a moment to take a look at it, we have the electrons and the nuclei and the oscillation that occurs between those two that's intrinsic to the high temperature involved. That oscillating charge leads to the emission of electromagnetic radiation, which we refer to affectionately as light. So that oscillating charge that produces the electromagnetic wave that then emerges from the surface of the sun has a very distinct shape to it. If we plot the intensity coming off of the surface of the sun against wavelength, that has a very intrinsic shape to it. And the area under that curve is exactly equal to the power that we calculated, which is the area of the surface times the Stefan Boltzmann constant times the fourth power of the temperature of that emitting surface. So when we do that simple calculation, we're summing up all of the emitted photons from the shortest wavelength to the longest wavelength. But this also has a name. It's called Blackbody Radiation. And the intrinsic shape of this is very characteristic of an emitting surface, whether it's the human body, a black iron plate elevated to high temperature, or the surface of the sun. Now, I should point out that when we look at the sun, we actually see absorption features that are created by molecules and atoms in the atmosphere outside of the photosphere. So the spectrum of the sun actually has a number of interesting features that modulate that overall blackbody radiation curve. But let's take a look at the electromagnetic spectrum for a moment. So when we discuss electromagnetic radiation, it's important to put this in context because, of course, humans are capable of seeing in the visible. That's why we call it the visible. But it's also true that the human eye evolved in concert with the temperature of the sun, because it turns out that the sun, the emission from the sun, peaks right in the middle of the human visible domain. And it's very easy to see why. When we have that sun as a source of light, we want our eye to be matched to that in the electromagnetic spectrum. But this visible domain is a tiny, tiny segment of the entire electromagnetic spectrum, because if we start out at a long wavelength, so lambda long, we have wavelengths that are comparable to the dimension of a human being, some 2 meters thereabout. And that's where radio waves occur. When we listen to AM or FM radios, that's the wavelength of communication. When we use our cell phones, we're in the domain close to microwaves, and the wavelength there is 10 to the minus 2 meters. That's about the size of your fingernail, extending down to the size of the head of a pin. Now the infrared domain, and we can see how important the infrared domain is. Our bodies radiate in the infrared. We receive infrared radiation from the walls, from the people around us, and radiated back by our clothes into our body that cuts the energy demand of the human body dramatically. And the wavelength in the infrared is about equivalent to the diameter of a dust particle. And as I have mentioned before, if we could see in the infrared, we would have solved the conservation of energy a long time before we did, because we would have seen mechanical energy converted to thermal energy that then radiated in the infrared. It would have solved the problem very quickly. But let's move on. Let's look at the visible domain, comparable in wavelength 10 to the minus 6 meters or thereabouts to a bacteria. Viruses are much smaller. They're 100 times smaller than a bacteria, and the dimension of a virus is comparable to the wavelength of an ultraviolet photon, and we'll talk about photons in just a little bit. Photons are particles of light. And then we move down to the X-ray domain, which has a wavelength comparable in dimensions to an atom. And finally, gamma rays that are coming in from outer space have wavelengths of 10 to the minus 12 meters. So that spans the entire electromagnetic spectrum as we will be using it. But there's one very important relationship, and that is this relationship. And that relationship links the wavelength of light the frequency of oscillation of those electromagnetic waves and the speed of light c. The speed of light. And the relationship is remarkably simple. If I multiply the wavelength of that electromagnetic radiation times the frequency of the oscillation of that wave, that's equal to the speed of light. And so that is one of the most fundamental relationships in electromagnetic propagation.